Okay, so we are on variables and constants. Whoops. Variables and constants. Okay. Hopefully this records all right. So, this is what a variable is. A variable is it's a construct that is common in almost every computer programming language. And whenever introductory textbooks on computer programming talk about it, they usually try to talk about it through some kind of metaphor. Think of it as like a bucket that you can put a value in and take something out. I think that's a crazy way to think of it. Especially because we're going to do some things in this class that if you've got just kind of a metaphorical understanding, it's good to know that the device is completed in something. If you have a metaphorical understanding only, it's going to be hard to really grip what's happening internally. So I'm going to take you through something that might feel a little painful today. When's the add drop deadline? Has it passed? No. You know, I think I'm realizing that's why I didn't used to cover this lecture so early in the course. This lecture might make your head hurt a little bit, but let me just preface this by saying I'm not going to expect you to be able to call back most of this stuff on any exam. So we're talking about variables. You have to understand what some of the different data types are and why you'd use one over the other. But the very low-level stuff that we're talking about, actually how memory is addressed, I'd like you to absorb this and say, oh, okay, that's interesting, but not necessarily feel like this is something I've got to be able to give back to me ever. Get a general feeling of how this works. So this is what a variable is. A variable is, it's a location in memory. So you've got memory in your computer. I mean, the physical hardware of your computer, when you look at the computer, I probably should have had that slide before. You've got a computer, right? There's physical hardware. What are we looking at? We're looking at the memory in a little memory chip in here. This is where you store information. Ah, good sir, how much memory do you have on your computer? Do you know? No idea. How about you? 16 gigabytes of RAM. Probably, if you have it in the teens, it's probably 18. No, it is 16, probably 16, 18. Or 8 gigabytes or 16.
I got 12 gigabytes online of RAM.
You got 12, yeah, so you're kind of halfway. Anyone have 32? I got 32 on my computer upstairs, and it's got another slot that I just think I should put another one in and get 64. But every time I look at how much memory I'm using, I'm not even using what I have, so I'm not going to do it. But you've got a lot of memory. So that's what we're talking about finding somewhere deep inside one of these chips, we're going to allocate a little portion of that, and we're going to say, we're going to put a value there. And we're going to call it back later. And so when we talk about a variable, it is a location in memory with a name. That's what it is. It's a named location in memory. 16 gigabytes. How much is that? 16 is a little bit more than 15, but what does that mean, 16 gigabytes? If you take the Book of Mormon, put it on the ground, and put another one on top of it, another one on top of it, and stack them up until you're higher than the Tanner Building, in fact, until you're about another 20 feet higher than the Tanner Building, you would have 16 gigabytes of RAM. You could take the full text of the Book of Mormon over 1,000 times and load it into memory on your computer. Just fine. That's how much memory you've got. Does that sound like a lot? It's like a lot to me. It's a lot of memory that you have in your computer. And so the question is, there are literally billions, that's 16 billion bytes. How are you going to keep track? How many do I want for that one variable? I want like 2 of them. There's 16 billion, and I got to keep track of where those 2 are. How am I going to do it? And the answer is that each one of those addresses in memory, the locations in memory, has an address. Now, if you've got a 64-bit operating system, then you can. That's what the address is where the 64 comes from. It takes 64 ones and zeros, 64 bits, to be able to address your memory. So much memory, you've got to have 64 bits to be able to have enough unique addresses for them all. If you have a 32-bit operating system, which is probably none of you here, we're probably almost all on 64 bits by now. But a 32-bit operating system, you only needed 32 bits to be able to access all of your memory because you couldn't have as much. You can have a maximum of 4 gigabytes of memory. I remember when I got my first 32-bit operating system, 4 gigabytes. Who could ever use 4 gigabytes? I think it was in the late 90s, mid 90s. So now you can't live with only 4 gigabytes. I don't know how that happened. And so you've got this long address. And it used to be, for a short time, it used to be that we referred to that location in memory by its address. So this is one little location in memory, it's got an address, that's where I'm going to put a value. That worked okay at the time because we didn't have multitasking operating systems. You have one operating system that's running the computer. And how many programs are you running at once? You're running one. And so when that program is running, it's the only possible program that can want that location in memory. But what would happen today if we said, you know what, we've got 3 programs running, and we're actually picking physical addresses where we want to be able to refer to that location in memory? What would happen if 2 of them refer to the same location? Can you imagine this? You put in something into one program, put something in another program, and it happens to write right over the top of the other one. You go back to the program, it's been changed. That was what the problem would be. Now, in our operating systems today, if you had a program that tried to do that, said, listen, we've got this memory here that's being used by Microsoft Word. And then we've got something over here like Tableau. Decides it's going to try to write to that same location. Your operating system is going to kill that program. I mean, it will just say stop. You tried to access memory that belonged to somebody else, no good can come of that. And it looks at that and goes, you're a virus. You're doing something naughty, and I'm just going to stop you from running. And so we don't care that we are on a particular little part of this chip. When we say, I need a variable, I need to be able to store a value, and then later see what it was, call it back and think about it again, I don't care where it is. What do I care about? I care that I have a certain amount of it, and that I can refer to it again. I don't care where it is. And so that's why it's important when we say variable, we're talking about it is a location with a name. The VBA interpreter, we'll show you the line of code that actually causes this to happen. But the VBA interpreter says to the operating system, I need 2 bytes of memory for a variable. The operating system looks across all of its vast 16 billion bytes of memory and goes, hey, there's a couple I'm not using. You can have those, no charge. Gives them back the address for that. And it does. The operating system sends back that 64-bit address. This is it. This is yours. The interpreter then binds that to the name. So as a programmer, I think of that as the name of the variable. I'm going to declare a variable as X. And then the interpreter will bind that on to the address where it's allocated. So when we say that is a named location, that's what I mean. Some location in memory that I refer to by a name. So that's what it is. What do I do with it? It's where a value of a particular data type can be stored and retrieved. That's what we're trying to do. Put a value somewhere, pull it back, and do something with it later. Questions? Yes?
So it is in one place, it doesn't ever move around, the variable will always stay in that particular address in memory?
That's a more complex question than you think you're asking. I'm gonna punt that one. We'll cover it today, but let me get a little more background before I answer it. The answer is yes and no. So when we talk about 16 gigabytes, we're talking about bytes, but that's not the lowest level of memory. Think about it. Everything, and you probably do this already, but everything that we do and work with in a computer has to ultimately be stored as a long sequence of 1s and 0s, right? You do that already. And so in memory, we've got to translate everything down to 1s and 0s. And so when we say a byte or 16 gigabytes, we're talking about a unit of memory that's 8 bits long. The lowest piece of memory is called a bit, and for binary digit, it's a 1 or a 0. But in VBA, we don't ever work at anything below a byte, and that's common for many languages. In fact, most languages. We're not going to work with 1 at a time. We're going to work with 8 at a time. And so, and each one of those bits can be a 1 or a 0. And so, the way that we keep track, let's first keep track of like an integer. How are we going to keep track of an integer in memory? So here's the part that, if your eyes glaze over a little bit like this, try to stay tuned, but don't feel like you got to keep notes on this. Just try to get the feeling for this part right here. So, those same 8 bits. One of these bits, I call it, this is the 1 bit. This is the 2 bit, this is the 4 bit, this is the 8 bit. And so if I want to be able to store a particular number, I just have to put a 1 in the location that corresponds to the number that I want to store. So I want to store 128, I just put a 1 over there in the 128 column, and then I'm good. If I just want to store 1, I'll put a 1 in the 1 column. Well, what if I want to store something that's like in between? Well, here's how I store 2, but what if I want 3? Yeah, 1 and 2. So I'm just going to take the ones of these that are selected by having a 1 in them and then add up their column value. Okay, so this is a regular binary notation. That's what a 4 looks like. We're okay with this? What's that? 65. That's 65, yeah, no problem, 65. Okay, what's that?
255.
Yeah, 255. Yeah, how did you do all that adding together so fast?
We're geniuses.
Well, yeah, what you really did. Let's see, can I point here so the video can see? What you really did was you said, what's the next number in this sequence? Double that, it's 256. So if you add everything up to the right of that, it's going to be one less than what the next number is. So that's how you can get to that a little bit more quickly. Now here's the question. If I've only got 1 byte of memory, what's the valid range? What's the range that I can store in it?
0 to 128.
0 to 255, yeah. So if it was 128, that would be a 1 here, and that would be zeros everywhere else. But if I have a 1 here, and then I have 0, and then I have 1s for everywhere, then I've got 255. There's no room for me to put anything else. What would happen if I tried to, it's completely full. What would happen if I tried to cram another 1 in there? What's the word? Let's say you've got a cup, and it's completely full. It can't hold anymore, and you put something else in it, what's going to happen? It's going to overflow. Hey, watch this. Let's just take a minute and come over here into VBA. Oh, you know what? We didn't actually get to this part yesterday to show, but when I'm going to make yesterday, I mean last time we were together, but if I want to make like a macro, I want to make a block of code to run together. We only looked at stuff in the immediate window, but I want to get something to stick around. I've got to put it inside a module. So if you want to do this along with me, you can, but don't feel compelled to. Insert module. That'll give you a module for starting in a blank workbook. This is the one I inserted on Monday. Today's our second day of class. And I'm going to write in. If it doesn't have option explicit up there, that's okay. I'm going to say sub. I'm making a sub procedure. That's the key word. I'll call it variable demo. Okay, here's how I declare a variable. Dim x. Dim is short for dimension. I'm going to allocate some memory, and I'm going to tell it how much to allocate as well. It's kind of a goofy word for it, but that's what it's short for. That's the beginning. It says, hey, I've defined the name of the variable. But remember, our definition of a variable is that what a variable is what?
Name location.
Yes, it's the named location in memory. So it is, here's the name, location in memory, of a particular, it's like to hold a value of a particular type. So I got to give the type as well. Here's how I give the type. Call it byte, as byte. There's a data type called byte. Can you guess how much memory it takes? 1 byte. Yeah, so it's actually the one that we're looking at right here. And so if I wanted to put, is there a question here? Is it case sensitive? And the answer is no. But watch what happens. I'm here in the editor. I'm going to give x, I'll put a capital X. X equals 255. Watch what happens to the x. Are you ready? It like lowercases it for me. So the variable names technically aren't case sensitive, but the editor is going to always put them in the same case for you. And then let me just print. You saw how we printed to the immediate window last time we were together, right? I say print, and then like now, and it'll tell me the system time. I can do this. I can actually, from a sub procedure, I can push a value into the immediate window by saying debug.print. So you remember that we talked about objects and properties, objects and methods. So I'm going to tell you under debug.print, one's an object, one's a method. Which one's which? Debug is the object, and print is the method. So there's an object. It's a thing that knows how to do. It's got some functionality built into it, and one of those functionalities built into it is called print. And if I give that something to print, what that object does, it puts it in the immediate window. It's really kind of a simple object. I'm going to print x. So what this should do now is that it should just allocate the memory. When this line is evaluated, the Visual Basic Interpreter says to the operating system, I need some memory. How much does it ask for? 1 byte. Operating system looks over its vast amount of available memory. It picks a variable. It picks a location, hands it back to the interpreter. The interpreter goes, oh yeah. Oh, Jaron, don't go! This is Jaron. He's a TA. You can go now. You can go now.
Oh, thanks. See you guys.
All right. He'll have time scheduled on his. He's actually the head TA too. So if you're getting grief from any of the other 2 TAs, go talk to him. We'll straighten him out. Okay. So this tells the interpreter. The interpreter says, "Hey, operating system, give me some memory." The operating system says, oh great, here's a byte. It gives them back the address to that location in memory. And then the interpreter says, all right, we're going to refer to that as X. So when I say X equals 25, the interpreter goes, oh, X, I know what that is. That's that location in memory. And then it gives the instruction to go put that value over in memory. What does it do? It does that. It puts ones in every single bit in that byte. And now, when I say print X, it's going to go, oh, you don't mean X. You mean the value that's in the variable named X. And then it's going to print that out. So when I run this, what should it print? Yeah, it should print 255 right out there in the window. And it did. Oh, it's always amazing when it does what I told it to do. Now, let me try to put in a little bit more. 256. Wait, what happens if you have a cup that's full and you put something else in it? It's going to overflow. Watch this. Whoops. Cancel, run. Overflow. Runtime error 6, overflow. You tried to put too much in, and what did it do? It overflowed. If you pick your computer up now and shake it around, you'll hear that little bit rolling around in there. So what really happened was we prevented the overflow from happening, because if we actually did that, it would have pushed the bit outside of the boundary where it went, and that could cause trouble. So the interpreter says we're not going to let you do that. It would cause an overflow. Okay. Oh yeah, I have a little controller here. So that's 255. Have the whole thing loaded up. Okay, so now let's suppose I want to do something bigger than 255. What does it take? It takes 2 bytes. Now, truth is, I could do it with just one more bit, but I don't deal with memory in less than a byte. And so if I want to do something bigger than 255, even if it's just 256, then I'm going to take 2 bytes. And so now I've got 2 bytes here. What does 256 look like? It's just, I've got a whole column for 256, so I've just got one there. What is that? I was like shocked. Someone did this so fast in the last class. Okay, before you tell me the answer, how would you figure out the answer? Give me the algorithm. Add what? 512 plus 256, 864, 32, 8. And that all adds up to 1,000. I want to start 1,000. That's what it actually looks like in memory. If I could put some kind of electron microscope in there and see what's going on. And I can see what the difference between a 1 and a 0 looks like. I have no idea what it looks like, but that's what it is. Okay? Is there ever going to be a test where I give you something like that and ask, what's being stored here? No. There's no test like this. This is just for you to kind of look at and go, okay, this is what's going on kind of under the hood. All right? This is so that when we get to the data types, you'll kind of understand why we are. So here's the one data type. It's called a byte. And it's 1 byte, and we have that there. What do I have stored there? I'm not even sure. 128, 64. You can add those up, we can see what it is. It's probably 65. Oh, no, it's not. It's 230. Yeah, it's way higher. It's higher than that because we got 128 plus 64, so 232. That's what it is. That data type, we talked about that already, is 255. We can have 0. So what's the range for the data type called byte? 0 to 255. You already saw what happens if I try to put 256 into it. What happens if I try to put -1? What is that, an underflow? -1, run that. It is still an overflow. So what overflow means is you tried to put something into that location in memory that doesn't fit. There's no way for me to put that in there. Try as I might, there's no way for me to represent it because it's outside the boundaries of what that data type can handle. And so that is the data type called byte. It's one I will expect you to be familiar with. What do I want you to know about it? It's for integers, and its range, this is one I want you to know, this is the only one I want you to know the exact range. What's the exact range? 0 to 255. Okay, another data type. It takes 2 bytes, and that data type is called integer. What kind of numbers can I put into the byte data type? Integers. What kind of numbers do I put into the integer data type? Integers. And kind of the same thing, except now I've got a range that is different. But this brings up another question. How are we ever going to represent negative numbers? How could we possibly do that? And here's how we do it. We say, all right, you've got some value that you're storing, but then you're going to add it to some arbitrarily low negative number as the starting point. Take an example. So here, in the byte. So integer data type can go negative. Byte, no negative numbers. Integer can go negative. So let's suppose I've got that 1,000 stored here in just by looking at the binary representation. When the interpreter pulls that number out from memory, it goes, oh, this is an integer data type. It's not really 1,000. I start off by going all the way down to negative 32,768, and I add on 1,000 to it. And so it would know this is negative 32,766, 31,766. That's how it does it. Do you really need to know that's how it does it? No. What you need to know is roughly the range for integer. Integer takes 2 bytes, and it's roughly plus or minus 32,000.
How could you get to positive 32,768 if you're always adding it to negative 32,768?
That's a good question. The question is, how could you ever get bigger than 0 if you're always adding to negative 32,768? And here's the question. Without thinking about the negative part, just what numbers could I store here? What is the biggest number that I can store in this? One less than twice this. So if I have all these ones filled in here, what number do I have stored here? Actually, this should be a 7. This is a typo in this slide. This should be 1 less than I have here. And if I add that, oh yeah, that should be just a 1 right here. This should be actually negative 1. I've got the math a little bit wrong here. That's going to get me almost there. But now if I fill all of these in, do I do that in this slide? Oh, I don't. But if I fill all of these in, then that would be positive 32,767. So the range for integer is roughly plus or minus 32,000. That I'll expect you to know that. Exactly how it implements it, I don't need you to know that or to be able to look at it and say, what is this really equal to? Because that all gets handled. But I'd like to have some inkling as what's happening underneath. Everything has to be zeros and ones. So far, so good? Okay, so now we can handle positive and negative integers. What else do we have to do? Decimals. How are we going to handle a decimal? So how could we possibly represent a decimal value? Here's the answer. We're going to use a portion of the memory to allocate the integer and a portion of the memory to allocate where the decimal belongs in that collection of numbers, that integer representation. Let's take a look. So now I'm going to take a part of the memory and I'm going to say, this isn't used for telling me what the number is. This is used for telling me where the decimal goes in the number. So I have shown here 3,574. That's 248 plus this, plus all these. That's what that equals. How many, and this tells me how, of those digits, how many are to the right of the decimal point? What's the answer? 0. Yeah, I mean, this is 0. So this is none of these digits that are represented in this portion here, none of these digits are to the right of the decimal. Now I'm saying, hey, I've got 1 digit to the right of the decimal. You'll notice that none of these other numbers change, right? Only thing I'm changing between here is this part here that keeps track of where the decimal point is. My digits stay the same, but now I'm saying, of those 4 digits, 1 of those is to the right of the decimal. What if this is a 2? 2 of them are to the right of the decimal. You see it? 3 of them are to the right of the decimal. So we call these kinds of numbers in computing lingo, we call these floating point numbers. Why are they called floating point numbers? I store an integer representation, and this part tells me where the decimal point floats to. It just goes to a different location. Floating point numbers. We have 2 data types. Oh, while we're talking about integers, before we get this, there's one more integer type I want you to be familiar with. What are they? So far we have byte and integer. There's one more. Long. It means long integer. And what do you want to know about that? It takes 4 bytes of memory, and it's roughly plus or minus 2 billion. You number the billions, 1 billion. You can't do national debt with that. There's other ones we can use for national debt. But.
You say 2 bytes?
No, long is 4 bytes. So byte is 1 byte, integer is 2, long is 4, 1, 2, 4. Does that pattern look familiar anywhere? 1, 2, 4? 1, 2, 4.
And the integer is like 2 bytes and plus or minus 30,000.
Integer is 2 bytes plus or minus 32,000. If you remember plus or minus 30,000, that'll be enough. If you go to plus or minus 32,767, good for you. Doesn't help anywhere. Okay, so we have two kinds of floating point numbers. We have single, I've shown this here in 2 bytes. There's no data type that is a 2-byte floating point number. The smallest floating point number takes 4 bytes. It's called single. It stands for single precision floating point number. Now, here's the question. What's the range for single? The range is much more difficult to express because how big the number can be depends on what? How precise. Because you get a fixed number of digits. And then how precise it is depends on how big you can be. You want it really precise? You can't go very big. In fact, how precise can it go? If you fill in all the, that's what it is, like that same number, but it can be all the way down to that amount of precision on a single point, or on a single precision floating point number. If I use 15 digits for the decimal, how big can it be? Not very big. Ask the question, I don't know the answer. With little work, we could figure it out with Excel. If we only had some way to kind of write a formula that we could plug in values that would change. So
you get 15 digits with a single?
You get 15 digits to the right of the decimal place.
16 digits total.
You know what? I'm not sure. I think there's, I don't know. The question is, we should be able to figure it out because it's going to be, it does take 4 bytes for the decimal point. So it's going to be 8, 9, 8, 24, 25, 26, 27, 28. So it's going to be 2 to the 28th, 2 to the 29th minus 1. That's the biggest number we can do. Anyone doing that in Excel? 2 to the 29th minus 1. That's the largest number we can represent, and then we've got up to 15 digits to say where the decimal point goes.
So a single is 12 bits of number and 4 bits of decimal.
12 bits. No, sorry.
Single is the floating single?
Single is actually 4 bytes. I'm not showing the whole single here. I'm just trying to show the idea of floating point number. Single is 4 bytes. Yeah. And then you have a double precision floating point number, which is 8 bytes. I don't know how much is used for the decimal, but you just figure, I need a really big floating decimal number. It's going to be double. Question?
So for where there's 4 bits for the decimals to write it. Sorry, 4 bits for numbers to write a decimal. Is that for just single precision, or is that for all floating?
That's for single precision. I don't know what it is for double precision. Presumably it's more. Yep.
On these floats, are they also subtracting half out of it? So that
Yeah. Same thing. You've got a positive and negative on these floating point numbers as well. Yeah. So kind of both of the ideas that we just talked about are covered in here. Question? This actually went much better than the way I used to teach this, which is kind of doing examples in Excel to get us there. But I didn't have time to do anything more. So let's talk conceptually about some other kinds of data types. There's another kind of decimal that's fundamentally different from the 2 floating point numbers. It's called currency. It's a fixed point number. So it can have a decimal, but the decimal doesn't float. The number is always recorded to 4 digits of precision. I guess they figure if you're keeping track of money, getting down to hundredths of a cent is precise enough. And so what that means is that it's the same thing. I've got a certain number of digits that I can record, but because it's always recorded to 4 digits of precision, how much memory do I need to keep track of where the decimal goes? Say it? 0. Yeah, it's always 4 digits. And so, I mean, if I actually want to show it as a whole number, I've got to put it in so that there's 4 digits. The first 4 digits, or the last 4 digits are 0. And so it lets us handle bigger numbers in a smaller amount of memory. But what we give up is the ability to say how precise it is. It's always recorded at 4 digits. Those are the numeric types that I want you to be familiar with. 3 integer types, byte, integer, long. 2 floating point numeric types, single, double, and then the 1 fixed type, currency. I actually think that's all of them. It's not like I'm giving you a discount here. Those are the numeric types And I want you to have the level of, what do I want you to know about those? How much memory, what the range is, what the name is. Yep.
Is date not numeric value?
Oh, that's another one. I didn't talk about that in my last class. So date's a date value. Like everything else, it's stored as a number. Everything has to get stored as a number. But date technically isn't numeric. It's a date. It's kind of its own type. That'd be a good one for us to talk about as well. In fact, let's take a little detour into date right now. Sub date demo. So let's say dim someday as date. That's going to allocate, so dates take, I want to say 8 bytes. I'm virtually certain that it's 8 bytes. Someone wants to Google that and let me know if I'm right or not. That'd be great. And then I can put a value into that. I will say someday equals today, equals now. Remember that we come to the immediate window and we say print now, then it reads that value from the system clock. So I've now put now into someday, and I'm going to print that. Debug.print someday. It should just print now. It should be a little bit later. This is 4:10:59, so this should be a little bit later. I'll run this one, and it actually prints that date. So I'm able to declare this as a date and plug it in there. But what it's really doing is it is keeping track of a certain number of days from an indexed starting date, which is January 1st, 1900. Which means, I'm kind of like showing things that we haven't really covered yet, but I can convert between one data type and another. Let me just show you this real quick. We'll come to the immediate window and I'm going to say print. And I'm going to convert to an integer, cint. There's a function built into the Visual Basic for Applications language. I can give it a number in here, 122.3. And I'm going to convert that to an integer. What is that going to print? Any guesses? No dates involved here. This is just, we're just looking at numbers right now. So I've got a floating point number.
122.
Probably going to print 122. Here's the hard one. How about if I do like 0.9? Is it going to round down or up? I think it's going to go up. Yeah. So we have convert functions. Well, I can convert a date. Let me convert, CLNG, convert to long. There's a data type called long, someday. Right, someday is just today's date. So what we're going to see is that that can have, and that will be the number of days. Someday. Since January 1st, 1900, 43,100 days. So the way the date actually gets stored is a number of days from an index date. Now, you'll notice the date actually has a portion of a day that's coming out here as, all the way down to seconds. Well, I convert it to long. What's long? Tell me what you know about the long data type.
It has no decimals.
No decimals. Just like when I converted that decimal number to an integer, it truncated it, or it got rid of the decimals. So what if I converted this to double? CDBL. Oops. Now it's still 43,100 and, this time it's 10.6. It rounded up. And it's that portion of a day that gives us 4:13 and 44 seconds. It's actually more precise than seconds. It gets down into milliseconds. It doesn't go all the way down to millisecond precision, but it goes down to like blocks of 3 milliseconds or something. So that's what a date is. It's actually storing a number, but it's just a number of days from that point. So what if we did this? What if we said someday equals C date? Let me convert to date. Let me convert 0 to a date. Well, let's convert day 1. And then we'll print someday. 12/31/1899. Oh, so I guess it's not from January 1st. It's from 12/31. It's from the end of it.
It's not in the book. It's 12:30.
It's 12/30? That's where 0 is? Yeah, because I put this to 1, thinking it would go to January 1st. Let's go to date 0. Oh, and when you do date 0, it thinks, oh, you just must be talking about the time. Yeah, let's stay on 1. Or -1. 12/29/1899. Yeah. So yeah, so it sounds like the origin in VBA is December 30th, 1899. There you go. That's how dates are stored. Did anyone check to see if it's 8 bytes for a date? I think it must be. It is? Yeah. Okay, so that's the data type. Okay, we have other ones to talk about. I really wish I had in this presentation the next type we're going to talk about. That's characters. Strings. How are we going to keep track of letters? Substring demo. Declare the variable. Dim first name as a string. And then first name equals Nephi. Truth is, at some point in this course, you're going to have to answer some question that says appropriately brought gospel topics into class, and you'll think back to this moment. You'll go, well, he did something. He did something. Okay, so first name equals Nephi. So the question is, how? Oh, how could it possibly do this? Numbers I get, but how does it do this? And here's the answer. The great Google will tell us. Let me look for ASCII. ASCII stands for American Standard Character ASCII Information Interchange, I think. What's that? Here's images. You know, any of these will do. How about this one? This one looks nice. View image.
American Standard Code for Information Interchange.
American Standard Code for Information Interchange. That's what ASCII stands for. American Standard Code for Information Interchange. Okay, so here's what we say. We say, listen, we got all these characters in the char column that we need to keep track of. Capital A. We need to keep track of capital A. How are we going to represent that in memory? Ultimately, it's got to be a bunch of 1s and 0s. How do we do it? Do we just put a bunch of them out there and kind of draw an A with 1s? A bunch of 0s and draw an A? That don't work? No. Oh, no. It doesn't go like that. What do we do? And the answer is we use this conversion. We don't have to use it. Excel, VBA uses this conversion table to say, oh, you want me to store a capital A? No problem. That's number 65. That's character number 65. I'm just going to store 65. How about capital B? 66. How about if you want to store a $? That's character number 36. See how it works? So if I was over here, let's come back to here and present again. Going back. Almost there. 65 is what? Capital A. That's how a capital A is stored. And so it takes 1 byte per character to be able to store that string. Now, if we think about memory, it's just one little bit after another. So So we start, you're starting right here at this particular location. We put in 8 bits and we go, it's 65. How could VBA possibly know when to stop? This gets to your question about, is it always the same location? How does it know when to stop? And the answer is that with a string, it uses a different amount of memory depending on what you're storing. And so there's a little bit of overhead involved with it. When I say, or when this gets processed, declare first name as string, 4 bytes get allocated immediately that just say, we've got to keep track of how long this is. And so when we say it's 1 byte per character, it's 1 byte per character plus 4 bytes. Given 4 bytes, you can then say it's 0 characters, the smallest string I can have 0 characters, Or I could have one character. And then in my first 4 bytes, I would represent the number 1. And then when the interpreter is going, okay, it starts at this location in memory, it reads the next 4 bytes and it goes, that's how many bytes I have to read. It looks at that first 4 bytes and goes, oh, that's a 1. It reads one more byte, it says that's the string. If it says, in those first 4 bytes, if it says 27, it goes after those first 4, reads the next 27 bytes, and it goes, that first one goes, oh, that's 65, that's capital A. Next one, 66, that's capital B, and it figures it out, and then it brings back that string. That's how we get the string. So let's suppose that I've got 27 characters, and then I change the value in the variable to something else. 80 characters. What's going to happen? Let's think about it. We got memory. The operating system is giving us 84 bytes of memory, or what did I say, 27? These 31 bytes of memory to keep track of the string. Is it possible that right here, after those 31 bytes, that memory is allocated to somebody else? That's totally possible. So can I just stretch that thing out? No. I mean, I might be able to. That might be free space, but that's not what happens. Every time I change a variable, what happens is the VBA interpreter asks the operating system for some more memory. What does it do? It says, guy's trying to put in these 80 characters, and it says operating system need 84 characters. Operating system looks around and goes, I got 84 characters. They have to be in a row. They have to be right after each other. Because I got 84 characters right here. There you go. They're all yours. And then we write that value into that location. We say in the first 4 bytes, we say 80, and then the next 80, we say the actual values that we want to store. And so for all of our numeric types, once it's declared, it stays in that actual location. For the type string, every time we write to it, it goes to a new location. But I don't have to keep track of the fact that the location is changing because every time the address comes back from the operating system, the interpreter binds it to the same name. It binds it to this variable name called first name each time. Got it? Are you ever going to have to give me on a test, oh, this is 65, that's capital A. You shouldn't have to memorize that. Would you have to look it up on a table? No. No, it's just, I want you to understand what's going on, but not understand it so deeply that it should ever be tested on it. I guess that means that's a pretty shallow understanding. We're not looking for deep understanding, but just have a notion of what's going on here. Questions here?
So according to the character codes, then there can't be more than 255 different characters.
Aha! Good question. Maximum of 255, and the answer is yes, maximum of 255. Let's look at that chart again. So there's a way to get past that 255 limitation, but let's just look at this one. So we go here, and in fact, we've got the first 128. Oh, I'm not looking at here. Oh, blast. View image. We've got the first 128, 0 through 127, that are standard. They mean the same thing everywhere. And then there's the extended set. Have you ever seen this? Where you look at a web page and like right in the middle, it's got some character that you go, that is not the right character. Isn't that weird? Have you seen that? Mm-hmm. That's because characters past 127, number 127, they can be different depending on the operating system or depending on various other things. So you get a higher number of that from a Unix operating system that comes over here to a Windows operating system, and it may not be the same symbol. And even depending on other things, and I'm not sure exactly what that is, the ones above 127, not necessarily guaranteed to be the same every time you look at them. But always from 0 to 127, they're the same. The first 32, 0 through 31, they're not even printable. They're these ones over here. They're used for like ringing the bell. This one's the bell. Like you print that character. I think it's character number, is it 7? Bell is character number 7. You print that and it rings the bell. Does your printer have a bell on it? No, old printers had a bell. Kind of like typing along and it gets to the end of the line and goes ding. Oh, I got to go back to the. Sorry, that's what it's talking about. So this goes back a long time. 9 is a tab, I think.
Line feed.
Horizontal tab. Yeah, 10 is line feed. 13 is carriage return. Right? Carriage. What? You're typing along. Ding. What has to happen? The carriage has to return, and what?
The paper has to go up.
We have to feed up by one line. We have to do a line feed. And so, in fact, even today, When I look at a text file in Windows, you look at a text file and you go, there's the end of a line, it wrapped down right here. If you say, I want to actually look at the memory that's there, all your characters are there, and it goes right there, and it goes character number 13, carriage return. Is it 13 carriage return? Yeah. Character number 13, and then right after that is character number 10, line feed. And then the next one is the characters that start for your next line. So yeah, I mean, it's kind of crazy. Do we really need 2 characters to tell us that's the end of the line? We could get by with 1. But in Windows, they still use the 2 because it goes back to the 2 operations that you had to do to signal that's the end of the line. Advance the platen and return the printhead. That's kind of weird, but this is the kind of legacy that we're living with. So yeah, 32 is the first printable character, and that's a space. So you go from there. Okay, we still got some stuff to cover. So that's string. We could just print this, and you'd see it really does print Nephi. I don't think we have to run that. You get it. Oops, first thing. Okay, let me throw another one in here. Usually, here's what I'm about to tell you. This is where the MBAs in the class often want to revolt. Okay. We've just spent an hour, more than an hour, talking about bits, bytes, and binary notation. Dim last name as, last name's kind of a bad one. Let's just call it data, some arbitrary name. Data, dim data as variant. The variant type, the variant type is magical. The variant type behaves the way you treat it. If you treat it like a number, it acts like a number. If you treat it like a string, it acts like a string. You treat it like an integer or floating point number, it just acts that way. That's kind of neat. It takes some overhead. How much overhead for a string? How many bytes? 4 bytes. How much overhead for a variant? For every variable? 22 bytes of overhead to keep track of this. That's the price you pay for being able to use to have one data type that rules them all. You might be tempted just to say, oh, great, I'm just going to declare all my variables. In fact, if you forget to put the as variant, it's okay. What does it do? Makes it a variant. You can release it. You mean you could just forget data types altogether and say dim your variable name and you're done? Yeah, you can. It costs you 22 bytes per. So what? I got 16 billion of them. Why care if I use an extra 22 now and then? You're killing me here. Here's the thing I haven't told you yet. Later on, I'm going to teach you how to declare 2 variables at the same time, or 200,000 variables at the same time. One statement can declare that many variables. And you'll keep track of all of them separately. In that case, does 22 bytes make a difference? Yeah, it does. So I need you to kind of understand this, partially that, and partially because you're going to be looking at other people's code, and I want you to kind of understand what's done in kind of standard code writing. But here's the thing. Data as variant. Is that VBA has a really complex set of rules about how variant works, and what is it going to do to convert things when you're dealing with variants. Let me just give you an example here. Let's say, what do you think I'm going to get if I add a print. What happens if I add 3 plus 3? What is that going to give me? What do you think? What's going to be an error? Yeah, 33, right? This is a string 3 and a string 3, and when I say add, it goes, oh, it just means you got 2 strings, you add them together. You can't really add strings, but I guess we'll let you concatenate them. What if one of these is a integer and one's a string? Does that even make sense? Take a number and add it to a string, what's it going to do? You got 2 possibilities. It's either going to make them both into a string, or it's going to convert the string to a number. What do you think? You don't know, do you? You don't know. VPA knows exactly what it's going to do. There's a whole set of rules that it follows. But anytime I'm working with variant, it's applying these kind of rules to convert to decide what to do. Not only do you not know, I don't know either. If I had to guess, I say this is going to print 6. I wonder if I just reverse the order. Plus 3. No, it still does 6. It goes, one of those is an integer. I'm going to look at that string and I'm going to go, I can make that an integer. And it makes it an integer. Okay? So that's the danger of working with variant, is that it's got all these rules that when it looks at it, it's trying to decide what it thinks you really meant, and it might be wrong. Okay? So there's a risk to just saying, not only is it going to use more memory, but there's also a risk. I don't know how you can even find out what all those rules are. I don't know if they're even ever published anywhere. I've never seen them. 3 plus taco. Yeah, what's it going to do with 3 plus taco? Oh no, just fine. I bet that's going to be perfect. That's right. And the three tacos for 99 cents on Wednesdays. That's what we should. What are you guys thinking here? I'm kind of surprised they didn't figure that one out. Okay. That's right. Hey, by the way, could we send a text message with Excel? Could we send a text message to Taco Bell? Yeah, we can. I'm going to teach you how to do that. Maybe not the Taco Bell part, but we'll teach you how to make Excel send text messages before we're done with this class. Okay, other things we got to cover still. Okay, folks, there is another data type. How many of you are going, so far, these data types aren't so bad?
Oh, yeah.
How many of you are going, is it too late to drop the class? Okay, so yeah, what we done so far? Okay, now, folks, what I'm about to show you, if you're thinking, yeah, I got data types, no problem, I'm checking my email, cut it out and pay attention. Because this next part, I need you all here for. We should sing a song from primary, head, shoulders, knees, and toes. Let's wake up. Okay, a little background for this one. Let's suppose that I've got this cell right here, B3. B3 is an object. Objects have what? Properties and? Methods. Good. Okay, so you got this. There's an object. Now, as soon as, how many cells are there on a worksheet? There's 1.04 million times, how wide did we go here? 16,000. There's a lot. Billions or more. So every single one of these cells is not actually an object loaded into memory right now. But as soon as I put a value in it, this one right here with a 12 in it, let's move this one around. That's too low down there. Let's put it over here. E6, that one right there is an object in memory for cell E6. That thing is now taking up memory. If they're completely blank, they're not changed at all, it doesn't really need any memory. But as soon as we do something to it, there's some memory involved. Yeah?
Is the memory location specified locked for each individual cell?
Is the location locked for each individual cell?
You just moved that from, what was it? K something to E6.
Yeah, I moved the value over there. I did not change the location in memory for the old L. Yeah, but I don't really know if it's fixed. Could something happen that caused it to change? I would think certainly. But I don't know. I don't know enough about the details about how it's implemented to know that. Okay, so let's refer to this object and make a change in code. Let's see if I can close these things down here. Give us a little more room. Subobject, demo. Okay, how do I refer to that cell? Range, what is it? E6. Range, E6. E6. And let's say I want to change three things. But I want to change the value. Value is going to equal hello world. I want to change the color of the font. Range.e6.font.color. There's like 16 million colors. I've memorized exactly two. Black, which is 0, and red, which is 255. Better make that bold as well. So font.bold equals true. And let me also then change the color of the interior of the cell. So we'll make that black. Okay, so when I run this, it should change the color of the font. It should make it bold, it should make it red, the background would be black. I'll run that, and it does all that. There it is. That's so fancy. Now, and this is all there was to it. We probably don't need object variables the way that I'm about to show you. But let's suppose that I don't have just one sheet. Let's suppose I got 3 sheets. I'm 3 sheets to the wind. What does that mean? Does this group know what the expression 3 sheets to the wind means? It's absolutely amazing. It's wonderful. It means you're completely plastered, falling down drunk. The fact that you don't know that gives me hope for this generation. Great. So I got 3 sheets here. So now how many cells do I have that are E6? I got 3 of them. I got 3 cells. How could it possibly know which one I'm talking about? It assumes the active page. So now, if I'm going to run this and I got 3 sheets, I got to be darn sure that sheet 1 is the one that's active. Otherwise, it could be the other one. Or I can specify the sheet. There's a bunch of sheets here. And on this, out of all these sheets, I'm not on the one called sheet 1. And on that, there's a range, and it has a value. I'm going to do that for all of these. Okay? Wait a minute. But wait, there's more. What if I got more than one workbook? Let me save this workbook. I'm going to save this in my documents. That's fine. I'm going to save this as an XLSM, so it'll save the code. And I'm going to call it variables underscore winter 18. Now I'm going to open a new workbook. File, new, blank workbook. And now I got a new blank workbook. So now, how many cells E6 do I have? I got 4. How many sheet 1 E6s do I have? I'm going to have to tell it which workbook I want. I don't want to type the whole name again. I'll make sure I get it right. Oh, by the way, question mark is a shortcut for print. I snuck that one past you. Out of all the workbooks, I want the workbook that is named this. Dot of all the sheets on that workbook, sheet 1. Yama Hamale. That line's getting really long. That line's getting painfully long. That line is longer than I want it to be. But wait, what if I have 2 instances of Excel open? I got to refer to the right instance of Excel, and then the right workbook, and then the right worksheet, and then the right... Oh, my heavens. I would open up 2 instances of Excel, but the code to do that is actually pretty complicated, and we only got 7 minutes to go. So, all of this, what this does, right to here, this gets me to an object, right? That object is somewhere in memory. That object is allocated, it's sitting, it's defined, it's sitting somewhere in memory. That whole part up there just gets me to that object. What an object variable is, it just allows me to remember that location. I don't want to have to do this whole thing every time I want to get to that object. I can just remember where that object is. It's just an address. It's an address in memory. If I've got a 64-bit operating system, it's 64 bits. It's a long address. 32-bit operating system, 32 bits to keep track where that memory is. So here's what I can do. I can say, let me declare a variable for this. Dim RNG as an object. And now I want RNG to equal that whole part that gets me down to that object. Now, how long can I spend on this next idea? It turns out that in VBA, the whole idea behind VBA is that it's trying to help. Most computer programming languages, it says, you got to tell me exactly what you want to do. And if you don't tell me exactly what you want me to do, what am I going to do? Nothing. I'm going to tell you I can't do that. Whatever you're talking about, even if it is so painfully obvious, the part I left off, it just goes, no. VBA has a different philosophy. VBA is intended to try to figure out what you meant. Let me print this. Print. Okay, what property am I asking it to print? None. I've gotten right down to the object. I've defined an object. But how many properties? It's got dozens of properties. It's got an address. It's got a value. It's got a font. What do you want me to print here? Most respectable programming languages would say what at this point? Yeah, I don't know what you're talking about. That's what it would say. Sorry, you got to be more specific. VBA doesn't. VBA goes, What's the most commonly used property in this situation? You're good at this game. Yeah, value. And so it goes, oh, my programmer, just a beginner here, but I got his back. I'm going to get the property that he must have meant. It's a little bit creepy. And so here's the problem. When we just have this expression by itself, the VBA interpreter is going, you left the property off, but there's a default property for this object. I'm going to infer that property. It's trying to help. In this case, it's not helpful. So what we're going to do, what we have to do, is we have to use the keyword set in front of this. We have to say set range equal to this object. And then by putting this keyword set here, it goes, you know exactly what you're talking about. No mere mortal would use the keyword set. You understand this stuff. And so I'm not going to try to figure out what you left off here. And so now, because I use the keyword set, now this variable is going to hold the address of where this object is. So it's got to calculate all this to figure out where that address is. It returns an address. And now we're saying, look, just remember the address. So now we can just say what? What do we put here? Yeah, RNG. This object variable will become handy for a couple of other things later in this course. But in terms of declaring and using the variable, that's kind of a pretty simple example. And now, we say, look, get us to the right range. It's a mess to get there. But now that we've got there, this code's not so bad. Change the value to this, the font color to this, the font bold to this. Question?
How deep do you usually need to go? You said that you could open instances of Excel, another instance of Excel. So
how much further can I go back this way on this one?
I guess my question is how far back do you usually go? Do you just do within the workbook? Do you just do?
Yeah. So the question is, should we go all the way? If we're just talking about a cell, should we go all the way back this way? And the answer is, if you know something about how the code's going to be executed, you might say, I know this is going to be executed by a user clicking on a button in this workbook. You could go, this workbook's going to be the active workbook. I don't have to specify the workbook. So typically for me, when I'm writing code and I know that's the use of it, I will go back to the sheet level. Identify the sheet I'm talking about, identify the range I'm talking about. Yeah. Okay. Questions? Yeah.
So if you were to use the recorder and you were to find something, you were to go to a different sheet or whatever, it'd put a lot more syntax in there, right? So it'd be like. Okay, here's the question.
We haven't talked about the macro recorder. That's coming up. So
I guess what my question is, you don't even have to explain it, but writing it like this, is that going to take less memory than what it would look like if you went through the recorder, where it's like selecting the sheet and then it's selecting the cell?
I'm going to answer your question, even though it won't make sense to everyone who doesn't know what the recorder is. The answer is it doesn't take more memory, but it will take more processing. The recorder way will take more processing. Because you have to activate the sheet, it records activate the sheet, and then it says go to the cell on this sheet, where you can say skip the activating and just refer to that cell.
So it won't take more memory, but it'll take longer?
More processing. It takes longer to process, but it won't take more memory.
How can you account for when you change the name of your sheet? So if you change the name of your sheet, is that going to...
Can I punt that, because I got to do something with the next 2 minutes. We'll cover that. We got a whole section that covers it. There's some great things that can handle with it. Folks, we're also supposed to be talking about a constants. And operators, chapter 7, operators and expressions. Quickly, folks. I'm going to have to leave chapter 7 to your perusal. Operators are like this. Let me print 1 plus 1. That plus sign is an operator, an arithmetic operator. Those ones are called operands. There's a bunch of arithmetic operators. There's a bunch of logical operators and or not. There's comparison operators, greater than, equal to, less than or equal to. And there are string operators. Concatenation is the main one. Last thing for the topic today, and that is there's a thing called a constant. Const, we call it pi, as single, here's the weird part, equals 3.14159. Is that with a constant is exactly like a variable. What's a variable? Named location in memory. What's a constant? Named location in memory. What's the difference? Constant, you set the value at the moment you declare it, and it can never change again. What if I wanted pi to be something different? Pi equals 3. I'm going to run this. You cannot make an assignment to a constant. You're not allowed to change it. And so you set it once, and it sticks around. So we can create our own constants. There are constants that are built in. VB blue. VB blue is just, it's a pre-named location in memory that's got a value sitting in it. Let me print it. VB blue. That's the number. See why I didn't memorize what blue is? 1671160. And yet when I run this, it's going to change that to blue. Okay, so some constants are built in. There are no built-in variables. There's a potload of built-in constants. And when you record code with the macro recorder, you're going to see a lot of these constants coming in. They're just names for locations in memory where Excel has already put a value there just so you can have it and use it by its name instead of its numeric value. No class next week. Thanks for coming. Class dismissed.